a short introduction to the task. So this is the energy storage task 45. The overall goal is to accelerate the market uptake of large thermal energy storage, which includes at least aquifer thermal energy storage, boreholes, pits, and tanks. And where this session is organized as part of the subtask 4, which is to disseminate the results and some information and technical content about large thermal energy storage. And this is the third Q&A session, and there are also like some webinars that we are organizing. To help me with the several questions that we've got, so we have gathered a group of experts. So there is Geoffroy Gauthier and Niels from Planergy. There's also Martin Christiansen Jorgensen from Aalborg CSP, Morten van Boa from Bobsol, and finally Sigrid Gelin from Geoenergicentrum. And basically, I will go through several questions that we've gathered since, some days, weeks, and months ago, and they will have to answer those questions. Yes, and I have just put in the chat a form that you can fill in if you would like to add some more questions, and then some links to the IEA Task 39 and Task 44 websites where you can see some deliverables and also like the recordings of the previous sessions. Yes. So we have identified 6 topics for this session, which are the market review, the LTES technologies, some questions about the PTES co-usage, some questions about the technology considerations and comparison, LTES planning, policy, and economy. And finally, if we have time and if we have the expert for that, the type of ownership. Some questions related to that. Yes. So we can basically start with the first question from the topic market review. The first question is the following: which technology appears most promising for widespread adoption? PTES, LTES, or PTES, and why? Is there one or several experts that would like to contribute and to answer this question?
I can start if it's okay.
Mm-hmm.
Okay. From my side, I think it's a little bit different question. Of course, each technology has its own advantages and disadvantages, obviously, and some are more suited for specific applications than others, and some are also more, let's say, suited for specific locations than others. I think the Netherlands is a good example of a location where the conditions seem more suited for LTES systems compared to PTES systems, and there already exist a lot of successful LTES systems in the Netherlands, for instance, and PTES or pit storages would be quite complicated in many places in the Netherlands due to high groundwater levels. On the other hand, pit storages, they are very comparable, you could say, to TTES or traditional tank storages from an operational point of view. And one of the big advantages is that you can charge and discharge with high capacities and change between charging and discharging very rapidly. So that makes PTES system very suited for let's say daily and weekly buffer storages as well as for seasonal storages. Whereas LTES system and especially borehole storages are more suited for, I would say, for purely seasonal storages. So with that in mind, I would say generally that, at least from my perspective, that PTES systems might be the most promising for a widespread adoption. Yeah, but as mentioned, for specific applications and specific locations, then LTES and borehole systems could be better suited. So from my side, that's not a clear answer, but in general, I would say pit storages are maybe a little bit more promising for widespread adoption.
All right. Thank you very much for this answer.
And I guess there would be other opinions on that.
And we're happy to listen to that if there's any other contribution. Yes, thank you.
Yeah, but to the most, I agree with you, Morten. But being from the Nordic countries, we have a slightly different perspective. LTES is a very, very good and effective technology where it can be done, but geohydrological conditions are not the right ones in most places. So therefore, I say LTES is probably the one that has the least possibility for widespread use outside of the Netherlands, which has a very special hydrogeology. When it comes to PTES and BTES, in the Nordic countries where we have so much crystalline rock as the ground type, PTES is probably less suitable for widespread use than BTES. It's easier in the Nordic countries to drill large-scale BTES than to make pit storage. But in countries where they have with large overburdens, soft overburdens or sedimentary rock, it's probably easier to do PTES in many cases, and the BTES could be more expensive due to regulations on grouting, etc. in those areas. So it's kind of hard to answer the question straight off. It really depends. I think you have to look at it from a national geohydrological point of view, and also as you said, Morten, it has to do with what you want to do with it. If you want large capacity, then LTES and PTES are better than BTES because they're dealing with water. The storage is in water, so they will have a possibility to have larger capacity than boreholes, which is a slower system. But if you're talking about quantities and energy quantities, I think BTES beats everything, because I mean you can use the ground to store very, very large amounts of energy over long periods of time, and you can still use the ground above it for other use. I mean, PTES has the problem that you are actually using the ground surface for it. LTES doesn't have that, but it can't be applied everywhere. Yeah, that's my thought on it.
Yeah, thanks so much. Jofa?
Thank you, Singhild, for this very thorough analysis. I completely share all of your points. We've had in our previous webinar the presentation about the LTES potential in Germany connected to district heating, and the preliminary conclusions were that there are not that many places that are directly suited for implementation of LTES directly coupled to district heating. So it is very geologically restricted. As you mentioned, you have to do some sort of national analysis and have an idea of the global geology of your country to know which technology would be most suitable. Maybe the one point where I would challenge a tiny bit what you said is, and it is indeed true that the surface usage of the different technology is a very important factor. For example, in Switzerland, they have both a lot of rock and limited space because it's a very densely populated. The cities are located in very densely populated areas, so they are more looking into BTES and LTES solutions rather than PTES. And at the same time, there is a recent development of looking at PTES where you can actually use the surface for something else, whether this something else is either to put PV panels on top or even to develop new designs with trafficable lids. So now this is looking into the future of the technology, but it is already happening. In China, for example, there is one thermal energy storage that is being developed that will have a trafficable lid. And there are several concepts that are being studied, but for now there is nothing that is established and a high TRL with regards to this, but it is coming. So it is something that might become available for PTES, and in that sense, it would put PTES in an interesting position to be implemented, as Morten said in the beginning, more or less in a more flexible way anywhere. And then the last thing about pit thermal energy storage, I would say, is that it can be put in old infrastructure. So that's also something that we're looking at in Task 45. How do we use existing infrastructure, whether it is an old mine or an old pit that was used for excavation of minerals, that can be re-employed to make some sort of pit thermal energy storage or an underground cavern or a mine. And these are also concepts that are being looked at, because, well, if the infrastructure is there already, why not try to reuse it to do a thermal energy storage? So I would say that it's a mix of all of those, but yeah, thank you very much for the inputs, both of you, Morten and Singhild.
All right, I think it's a good. And all contributions properly answer the question. I guess we can move on to the next one. Is there a need in industry or business opportunity for LTES in supplying heat for industrial processes? Who would like to answer that one? Yes, Jon?
Yeah, there are different opportunities. It sort of looks into the first question. It depends on the purpose. The different opportunities could be looking into connecting them with, for instance, data centers. It's industries where we want to decouple the demand and supply, and that makes good sense. So in terms of also other industries, for instance, power to X could be interesting to couple these large thermal energy storages with. Different opportunities. It purely depends on the purpose and what kind of agreements we can achieve, because we want to also consider, when we couple the large storages, we want to make a revenue stream out of it as well, or cut some costs. So all of this, if there's a basis for all of this to be combined, then yes, there's lots of opportunities, but it needs to be investigated. We are looking into different opportunities together with clients on this topic as well.
All right, thanks, Jon. Singhild?
Just a short comment. I think I think the question should rather be whether there is a potential rather than a need. I think there is a huge potential for LTES in industry, but it seems like the industry does not see the need. It doesn't have to be a contradiction, but in that. But I think the potential is there, whether they see it or not. The other thing I'd like to comment on that is that one of the problems with the industry potential, or the industry need, or whatever we should call it, is that industry tends to have very short requirements of very short payback times. So since all the LTES technology tend to have a rather long payback time, I think that is a disadvantage of the technology. So that's why, I'd love to see it happen. I love to see LTES fill its potential in industry, but I'm slightly doubtful it will happen because of this industry requirement of very short payback times.
Yeah, very interesting. Geoffroy?
I completely agree with Singhild. That's something that we have seen in IEA Energy Storage Task 41, Economics of Energy Storage, where we have gathered some renewable energy projects investors at workshops where we were talking about large thermal energy storages, and that was one of the things that came up, and that's something that comes up more or less every time we talk with investors in this field. So that's definitely one factor. I would add another factor to this is that the temperature requirements are also a challenge for large thermal energy storage, because industry has some needs between 50 and 100 degrees Celsius, but there is also a big portion of industrial needs that are above this. And for that, these LTES, they're suited for most common and cheapest technologies up to 100 degrees Celsius approximately. And then if you invest a little bit more with pressurized tank thermal energy storages, you can go up to 150 degrees Celsius, roughly. But then above that, there is no LTES technology currently mature that helps with this. That is with the kind of LTES that we're looking at in Task 45. If you want to look at higher temperatures, then you have to look at other concepts of thermal energy storages. High temperature, that's when we go in the range of high temperature thermal energy storages. And for that is a completely new kind of field. And there is actually a big interest from industry in that field, but it's much less of a focus of our task, I would say.
All right, thanks. Last comment from Morten.
Yes, thank you. Just to add, I completely agree also with Singhild that I think the biggest bottleneck is the investment horizon. We are used to see these very long investment horizons in district heating projects. But anyway, I have seen a few projects. They were mainly related to dairies or malteries or breweries. They typically have a large drying demand. And there we could typically use, for the first step in the heating, we could use LTES and renewable energy, and then you would boost the temperature with something else. But it always come down to the payback period. If they see into more than 10 years of payback time, then they are not interested in general. So there's a huge potential, but it's difficult.
Right. Thanks for that. So let's move on to this third question about focusing more on the LTES technologies. So the question is the following: how important it is to prevent oxygen from entering the treated water in a PTES? What are the main problems oxygen may cause? Yes, Niels and then Morten.
Yes, the thing is that we cannot keep the oxygen out of the water in the PTES because the liners are diffusion open. The reason for not want to have the oxygen in the system is that we want to avoid corrosion of black steel. So when we have the high oxygen content, which we will get over months and years, then we need another way to prevent corrosion, either using different materials or using very, very clean water. So it's difficult. So the main problem is corrosion, and secondarily maybe also bacterial growth in the system.
All right. Thanks, Morten.
Yes, I fully agree with Niels. So the short answer, it's not possible to prevent oxygen, and it's also not important or not necessary because the systems just needs to be designed to accommodate this. I would like to add to Niels's comments that you were mentioning that especially for carbon steel, it's a problem with corrosion, but also in the applications where we use stainless steel, it's still an issue, because you would have also corrosion in stainless steel if you have the combination of oxygen, high temperature, and an amount of chloride content in the water. But there will also be two other issues related to the oxygen or the air in the water. The one is it can also have an impact on the liners that we use to seal the storages, because it will accelerate the aging, or it could potentially accelerate the aging of the materials that they are exposed to oxygen, which oxidizes the material. And the last one is that we also, especially in some of the early storage application, we saw it as an issue that when this air or oxygen gets dissolved from the water, when you heat up the water, then there is a risk that this will collect as large air balloons below the cover. I would say this is also handled in the most recent applications, for instance, with the cover installed in Høje Taastrup and in Dronninglund and in Marstal. So it's something that you need to take into account, but it's something that you can take into account in your design, I would say.
All right, thanks. Any last comment, or should we just move on to the next one? Yes, Martin, or last comment? Oh, you're muted. We cannot hear you.
Sorry, it's because I'm sitting with Jon, so Jon has to unmute me.
Okay.
It's just more also one of the reasons why we decide to raise the pH value up to 9.8 in some of these PTES is also that we then lower the corrosion value by adding some of this sodium hydroxide or natrium hydroxide, so the pH gets a bit higher. So it helps to prevent corrosion of the pipes, as Morten and Nils mentioned. So, but just a little add to that.
Yeah, perfect. It's a good transition to the next question, actually, which is, what are the typical properties of the storage water used in PTES system? And how is the high pH level, such as 9.8, for example, achieved, and which base is added to reach this value? And there's also a follow-up application question, which is, given that the storage water has a pH of 9.8 and the temperature of 90 degrees, could vapor diffusion through the cover have an impact on the soil and vegetation placed above it? Yes, Martin.
Well, I guess I can continue on what I just said, that we add this sodium hydroxide into the PTES water to raise the pH value. And I talked to one of the operational guys from Dronninglund yesterday, actually, regarding this question, where he mentioned that they add this chemical, and it's basically done with a pH measurement, where they then see, okay, now the value is starting to fall, so they add some of this chemical into the water, and they need to have at least a certain amount of flow into the PTES before they can actually add this. And he mentioned that the flow should be around 50 cubic meters an hour for their PTES, but of course this is also PTES specific. And you can probably also assume that the pH value sort of stays in sort of these temperature layers in the pit. So the pH value might be a bit higher at the bottom, for example, and lower at the top. So this flow is sort of required to almost mix it up a bit without mixing it, because we don't want any mixing the temperature. So it's a bit hard to control where this sodium hydroxide actually enters up in the lid. So, and just to the additional question, I'm not aware of any soil problems or vegetation problems around the PTES in the embankments of the running plants that we have, but I don't know if some of the other experts had some more knowledge on this. So that's it.
Right. Thanks, Martin.
Yes, thank you. I would like also to address in the task 39, there was done some work, and there was also a deliverable describing or giving some requirements for the water quality for water used in PTES systems. And just to make it short here, it's at least the recommendations there is that you should treat the water in a reverse osmosis system to remove chloride contents and to have very low conductivity of the water. to avoid corrosion again. But also this also has the advantage that when you use sodium hydroxide or any other thing to raise the pH value, when you have very clean water from beginning, which you have if you treat it with reverse osmosis, then you need a quite small amount of sodium hydroxide to change the pH level. So that's a big advantage. And then for now, I'm not a chemist, but at least I was told that when you have, I think the issue that is addressed here is that when we have this water vapor permeation through the liners, would it then harm the soil if it's a high pH level? And according to what I was told, the water vapor that permeates the liner is not with an increased pH level, even though the pH level inside the storage is increased. But maybe some chemist can elaborate that.
Yeah, thanks, Niels.
I'm also not a chemist, but I will agree on that it's water diffusion and not the solvent inside the storage which will diffuse through the liners. And for the water treatment, we also take out the calcium, and we normally do that before the reverse osmosis, and that's because we don't want any deposits in the heat exchangers.
All right, thanks. So far, last comments.
Yeah, it's just to say if we think rationally, when the water is able to go through the membrane, it's because it's in form of vapor, and vapor does not contain any salt as such. So because this pH is increased because of salt content, then when it evaporates, it's pure water that goes through the membrane and not the salts that are in it. So indeed, it should not be anything else than H2O that goes through the membrane. But I'm also not a chemist, so I cannot 100% confirm that, but I think that's pretty good assumption to make.
All right, thank you. The next question is...
Maybe I could just add
go ahead.
that the liners are also used for landfills, and here they actually act as a chemical barrier.
Okay, thanks.
Yeah, and Romain, just before we go to the next question, I'm sorry. There was in the chat, I was just about to post the deliverable that Morten was referring to. So this is done now. You can find a very long report about water quality in pit thermal energy storage. But there is also a comment from Thomas Lapta that in this German research project called Efficient Pit, they are looking into this corrosion of parts inside pit thermal energy storage, and they're looking into a specific design of polymer discharging pipes that includes diffusion possibilities. So that's the first of its kind, and that's something that will be published and will be shared within Task 45 when these results are available. So that's just a complement to what was asked about the corrosion earlier. Thank you, Thomas.
Yeah, thank you all. Yes. So the next question is, for some context, it's about the PTES in Meldorf in Germany. A PTES system was built featuring a newly designed cover insulated with foam glass. And the question is, what is the performance of this cover, if there are any investigations that have been done, and have any operational issues been reported? Additionally, how are drainage and outgassing handled in a flat cover configuration? Does any expert have anything to say about this question? Yes, sure.
I think that unfortunately we don't have any of our experts that have worked specifically on this cover from Meldorf, but it is something that we can try to figure out for a Q&A further in time. So maybe unless I'm mistaken and someone knows a bit more about this, we can put this question to the side. And oh, I see Thomas Slapta has a hand up. Yeah. Do you know a bit more about this?
So maybe again the question with regard how is the functionality on the cover, right, on the lid with the foam glass.
Yeah, it's if you have some information about this, the foam glass insulation. Yeah.
So more or less what we have not the data which we should expect, or the current situation on the storage is that they cannot load it like expected up to the 90 degree because the heat from the waste facility is still not there like expected in the first phase. So they're currently working on include rotation heat pumps and so on, that they can then utilize the storage like expected with temperatures up to 90 degree, and then we can follow up on how is the functionality of the storage lids. That's more or less the situation at the moment at Meldorf. We have a similar storage lid was done in Bracht. This storage was commissioned and started operation last summer. So we have the solar thermal, the heat pump, and so on, and or especially the heat is coming from the solar thermal. So we will see, I guess, this year how it's performing, because I heard the last year they go up to over 70 degree on the temperature in the storage. So this year we will have a full cycle on loading the storage, and then we get the data on the functionality of that. So that's at the moment.
Okay, and that's about the actual practical experience with this. Do you know the theoretical expected performance compared with what has been used so far? So this PE foam and this XPS, for example, in Høytostrup and Dronninglund and Marstal?
More or less, to be well general, what we searching is for a stable high temperature resistant thermal insulation, and what is expected from the foam glass, more or less. It's a plate. You can place it. It's also a handling topic is also included in that, because you can also use the foam granulate, but then you have the topic how to compact it on the lid. It's more or less not possible because it's a floating liner on that. So that was the reason why they chose the plates, and we see it as a very stable material, and also resistant to the very high temperatures. That was the reason why I was the owner and the consultant, the planning company choose this material. Yeah. And included it as a first layer, and then up they choose different materials also to see. Then you go up to with pure materials, and then also XPS, what we know also from the other project.
All right, thank you very much, Thomas and Geoffroy. Yes.
Yes, this is not an answer. This is a question to Thomas. Do you know whether the humidity inside the lid has been measured?
Not really. What I know in Bracht, there's the University of Kassel included the measurement concept, so I don't really exactly. I know they have measurement system around the storage in the ground. I'm not sure if they also include measurement system in the lid. That's because the lid in Meldorf and Bracht is more or less very similar. In Meldorf, there are no humidity is measured in the lids. That's what from my point of what I'm know. Yes, that's more or less. it's not measured in Meldorf, what I explained before. Currently, we had not the high temperatures that you can look. What they include, there are a lot of inspection shafts that you can have a look inside of them. So maybe you can then also, if there should be humidity, you can also has the possibility to take it away, so that there is a built-in parts in the storage on the different levels and on the lids that you can more or less control this humidity and have always the possibility to have a visual inspection on that. That is what was more or less the idea also in the lid system.
Thank you. And then I can recommend making a thermal picture from above. We have done that in Høje Taastrup and Dronninglund, for instance, and it gives valuable information about thermal bridges and so on.
I agree, definitely. It's also what we also should do in our research projects, because we also evaluating some different solutions on the lid and to different materials and more or less. So what we definitely, because within the efficient pitch project, we also include different materials and like the PE foam and the glass, how it's in English, expanded clay glass. No, it's not the clay. It's a glass foam granules. Yes, and there's a measurement system in the lid, which is carried out by Solitas from the research side. So we will measure the humidity in the lid in the system. So more or less, there are big mock-ups which make it possible to measure the situation, the condition in a lid under real conditions. That is from laboratory to a lid completely outside, done under real conditions. And we expect to have, within this year, the results on that.
All right. Thank you very much for the discussion and contributions. I guess we should move on to the next question, very short one for Box CSP. Is it possible to share an image, maybe in the chat, of the pumping well and filter used in our Box CSP's cover design?
Yes, it is possible to share this. I don't know if I posted in the chat, if it's possible to see in a big enough size. This is more or less just a cross section of the pumping well, where we can see, of course, the different, what do you call it, dimensional aspects of it, and basically the weird triangle shape is the bottom that will be floating on the liner, where in the bottom you have some small holes. Yes, exactly. So the other guys can see it. Where on the bottom where it says 800 millimeters, there is some small holes, so all of the vapor that might go through the floating liner can actually enter the pumping well, where your mouse is pointing is now, where the pump will be placed, and then it can of course get the rainwater out. And in the chambers around the cylinder shape in the middle, they will be filled with gravel. So we have this as the lowest point in the lid, in each section for the Aalborg CSP solution at least, where then the water can flow into the pumping well via the holes at the top. And then to the sides of this shape, there will be some insulation, and just at the top you will have the gravel. It's a bit hard to explain without the mouse to point with and some other pictures, but here at least is the picture of the pumping well. And I can also share a full, sort of get the There's the other picture. This is just seen from above, where all of this would basically be covered by gravel, but then the lid is visible while you're walking on the lid, so you can inspect the pumping well and see if there's any water in it. Hopefully that gives an insight to it.
Yes, it is, and we can also put more information and maybe like some arrows on the sketch on the website later on.
Yeah,
could be interesting. Thank you very much. Yep. The seventh question is the following: how is water overflow managed in current PTES system? In other words, what mechanisms are used to discharge excess water from the storage? Yes, Nils.
There are two things to consider. One is if you want to make a controlled lowering of the water level, and then you're just using the in and outlet system because that's connected directly to the water body. So if you have a valve in your pumping well, then you can just open the valve and take out water. So that's very, very easy to lower the water level. But the other question will be, if there's too much water in the storage, what will then happen? If you're putting too much water in, or there's a lot of rainwater on the top of the lid and so on, where will the overflow come? And the answer to that is that the bottom liner and the floating liner are not welded together, so the water will be squeezed out between these two and into the embankment. And then you can design the embankment to handle water coming out there. But that will, under normal conditions, never happen, because it will take time for the water to build up, and you have much time to react and to take water out in the storage up front.
All right, thanks, Nils. Martin?
Yes, thank you. Just to add to what, or to emphasize what Nils said, that during normal operation there is no overflow to manage. There will be no overflow during regular operation. Of course, there will, or typically we accept that the water level will change according to the operation. So when the storage is fully charged, the water level will be higher compared to when the storage is fully empty. But these changes in water level will be maintained within the normal operation. So you don't have to take water in and out on the normal operation. Of course, if due to some evaporation and some water vapor permeation through the liners, you would typically need to add water during operation. But unless you do some mistake, there should not be any overflow.
Right, thanks. Yeah, Jean-Paul.
Maybe a question to Nils, because the way you follow up on the amount of water that is in the storage, or at least one of the ways, is by having this sort of well just outside of the storage where you actually measure the level, and that's a direct connection to the water that is inside the storage, but through the embankment. As far as I remember, for example, in Høje-Taastrup, there is this system of communicating bays where you actually have this water. Could that be an opportunity or a possibility to extract some water? Because if you open the lever measurement system in a way, you could extract water directly from the storage through that hatch. Is that something possible at all, or?
Of course, it could be done, but it's not dimensioned for that. You cannot take huge amount out because we have a very small pipe in that situation, because we don't need more than a small pipe for that.
Okay.
So again, taking water out in a controlled way, we will normally just use the bottom diffuser and the pipe connected to that.
Good. Thank you.
Thanks. And the last question regarding the LTES technology, this time about PTES. So the context is the following: we are currently evaluating thermal energy storage options for a district heating and cooling network. Our energy model indicates that the optimal energy storage capacity is 12 megawatt-hour, corresponding to a volume of roughly 400 cubic meters. We are therefore considering two design options: one single 400 cubic meter tank, or 2,200 cubic meter tank, all tank constrained to the same height due to planning requirements. And the question is the following: water for a same total volume is a single larger tank inherently preferable to two smaller tanks, or are there operational drawbacks or design challenges associated with with using one large tank instead of multiple or two smaller ones? Perfect.
Yes, I think the general answer here is bigger is better, especially in tank thermal energy storages. The bigger you get, the cheaper it is in specific costs. So, and especially in this range, the prices decrease significantly when you go up in volume. Another advantage of using a bigger tank than two small tanks is that you have less specific heat losses, because the surface to volume ratio, so heat, like outside surface of the storage versus the volume that is inside, is decreasing. So you would also have less heat losses. And then unless you really need to have two tanks that operate at a very different temperature, or you have, let's say, different operations for the two tanks, then I would definitely recommend to go for one tank of 400 cubic meters. Also because one tank of 400 cubic meters can operate at different temperatures in the different layers. So you just need to design it properly with the good amount of diffusers, and then you will be able to do the same. So my first answer is, as much as possible, do a 400 cubic meter tank rather than two small tanks.
Nils, what do you think?
Yes, I totally agree with Jafar. But I like to add also that having more than one tank in open connection with each other, you need to control the water level in the tanks. So one tank is not stealing the water from the other tank and so on. So it's a little more complicated to have more than one tank in the same system. It can be done, but it makes a little more complex.
Mm-hmm. Thomas?
Yes, thank you. I totally agree what has been said before. I just want to add one additional point, especially in this size. 200 or one 200 cubic meter tank can be prefabricated in a company and transported on site, whereas 400 cubic meter can be above the size of what can be transported on a road. So this could be an argument for splitting up into two 200 cubic meter tanks if it's in the end cheaper than fabricating one tank on site.
Yeah, completely true, Thomas. It's a very good point. Although we have to say that prefabricated tanks can go up to 1,000 cubic meters. As we've seen, actually, we've seen an example of this in Denmark, but it does require that you have the road access that enables to go around with such a tank. So that also needs to be taken into account. These small tanks might be able to be prefabricated, and therefore easily brought to the construction site and very fast installed. So all of these factors need to be taken into account when actually planning for the implementation, the duration of the construction, how long it takes to install, and how much it will cost as well. Yeah.
Yeah, maybe one addition. I wonder a little bit about the 1,000 cubic meter. I have the experience that the limit is somewhere at 250, 300 cubic meter. I mean, the main limitation is a maximum trailer width of about 4 meters, 4 to 4.5 meters that is allowed to be transported on a road. And for 1,000 cubic meter tank, it might be possible in some very specific situations, but for normal transportation, this is according to my experience, much too large, but should be checked individually.
I will share with you directly this reference.
Thanks a lot. I'm interested.
All right, Martin.
Yes, another comment. I also agree with what has been said, but I would like to hear maybe also comments from the others, as this is a cooling and heating network. If that would and if one of the tanks is expected to be used for cold water, and the requirements for cold storage would be slightly different compared to the requirements for hot storage. If that might, in some cases, then what your opinion is on that? If in some cases it would make sense to separate it into two different tanks, as the insulation would not be would not be needed with as much as insulation on the cold tanks, and you would maybe have some other requirements for the coating and the corrosion protection for the cold storage and so on.
I think it's an interesting question, Morten. We're going much more into detail, but to give a quick answer, we have worked on some projects of tanks that are double usage, and it can be rather easily handled. The easiest way to handle it is to have the same insulation everywhere, even on the bottom part that has less potential heat loss, just because it's easier to build it uniformly vertically. And then it's very easy to make a specific coating for corrosion resistance on just one part of the tank, whether it's 1/3 or the bottom half that will be used for cold temperatures, and then the top half that will be used for hot temperatures. So it can be done, and we have some examples of tanks that are designed in such a way. So it is possible to do. It does require a bit of specific design, but it can be handled.
All right, Nils.
But I think if the cold side and then the cold water is separated from the warm side and the warm water, I think having two tanks would be a good technical solution also.
Yeah. All right. Okay, now we're moving on to the next category, PTES core usage, with one single question. Are they companies that have implemented or tested PTES systems where the lead serves a secondary purpose, such as integrating PV or functioning as load-bearing surface, for example, like parking space, and how feasible it is to adapt a PTES lead for such dual-use applications? Martin?
Yes, thank you again.